Hello everyone and welcome back to another Physics Friday. And today I actually want to start with something that you'd probably ask in philosophy as well, but it's basically why. So we have this star right here. Say this is the sun. This is the sun. My question is why is it not collapsing in on itself? We have gravity pulling in here like this. Why is it not collapsing on itself? And the answer to this question relies on the fact that we have something called fusion. In fusion, we have a hydrogen and we have another hydrogen, and they come together and we get helium. A very accurate diagram indeed, and scientific. But basically, the whole reason why the sun doesn't collapse in on itself due to gravity is because, well, of fusion, of this fusion reaction that creates an internal pressure that counteracts the force of gravity. But then if we go over to, say, a slightly different star, say we look at a white dwarf, for example. I'll draw one real quick right here. Not to scale, but you get the point. We have this white dwarf right here. Well, in this little white dwarf right here, we don't have this fusion reaction going on. In fact, there's no real reaction going on inside at all, or anything resembling fusion. What we have is, we still have gravity pulling in, so why do these stars not collapse in on themselves? And the answer to that relies in something called electron degeneracy. And it basically relies on this idea that we have a bunch of electrons. We have a bunch of free electrons roaming around within the star. I'm not going to draw them. I suppose you can use your imagination. But it's basically a giant electron gas, more or less. And it's a giant plasma ball. And one thing that we have to note about electrons is that they obey the Pauli exclusion principle. And what that basically states is that if we have two electrons, so I'll draw these. We have two little happy electrons here. What Pauli's exclusion principle says is that these cannot, if they're in the same subshell, they cannot be in the same, they cannot have the same spin. So this cannot be a spin up, and this be a spin up. The second one would have to be a spin down. And what this forces the electrons to do in these white dwarfs, in these giant plasma balls, is since the lowest energy state is already taken up by electrons, it forces other electrons to go up into higher energy states. So say this is the ground state right here. That's the ground state. And say it's the first energy level. Above that, well, we're going to be forcing electrons to have basically more energy than they would like. And because of that, we get this external pressure and this external force basically counteracting the force of gravity for these white dwarfs. And just to finally get to the point of this video, I suppose, what I want to do is basically calculate the radius of a white dwarf using electron degeneracy pressure. And then what we'll do later is basically it's the same formula, but for neutron stars. So yes, let's get this properly started now, shall we? And the first thing we're going to do is note this, that the energy that these electrons carry is equal to, so E is equal to, and we're assuming this is non-relativistic, just for reference. What we have here is that E is equal to h bar squared times 3 pi squared nd, and I'll explain to the 5/5, and I'll explain what these variables mean in just one moment. And we have all that divided by 10 pi squared over m, and then times v to the negative 2/3. And basically just to note what some of these things mean. So we have our n here. Our n is just our number of nucleons, so our number of protons and neutrons within our given volume right here. And then d is basically the number of free electrons per nucleon, basically. So yeah, that's basically the definition of our terms. So what we can do here is that if we want to use this formula for, say, a star, well, what is a star? It's a sphere, basically. So that just means that our volume here is just, well, it's just volume of a sphere, and we know that. That's just 4/3 pi times the radius cubed. So we can sub that in, right? And it's gonna get quite ugly, but I promise we can calculate it out. So we have here then is a h bar squared still times 3 pi squared nd to the 5/3 over 10 pi squared m. Then we have this v to the 2/3. I'm just going to kind of write this off to the side for the sake of not making the thing on the left that messy. So we have v is equal to, v to the negative 2/3, pardon me, is equal to, it's going to be 3 to the 2/3 over 4 to the 2/3, well, I'm just going to write that as 2 to the 4/3 by properties of exponents, times pi to the 2/3, and then times r squared, again, it's by properties of exponents. So subbing this in, what we get is a 3 to the 2/3 on top, and then on the bottom I'm just going to throw the rest in. So we have a 2 to the 4/3 times a pi to the 2/3. And yes, I know we have multiple terms with pi, and I'll maybe simplify those out later. But for now, you get the gist. So what we have now is our energy, basically in terms of our radius. Because ultimately, what we want to do is given, say, the mass of the sun, let's calculate the radius. It would be as like a white dwarf. And we have this as a function of r, right? But we do have to note one thing to actually calculate this radius, and that's the fact that we don't just have this external pressure. Obviously, we also have gravity, and what this basically means is that our total energy, right? So we'll say E tot. It's going to be equal to this E, but then also our gravitational energy. So before I write out E total, I'm just going to note to the side that our gravitational energy, our gravitational potential energy basically, is equal to negative 3/5 G times m squared, where actually this is technically a different m, so I'll make it capital. M squared over r. And that's our gravitational potential energy, meaning that our total energy right here is just this plus our gravitational potential energy. So let's get writing, shall we? I'm going to write this in a more simplified form, just so you don't have like multiple 3's, multiple pi's floating around everywhere, just for the sake of being succinct. I hope I use that word right. So we have 3 to the 7, cross the 7 properly. 3 to the 7/3 h bar squared times pi to the 2/3 times nd to the 5/3, and then divided by 2 to the 4/3 10 m r squared, and then I'll write this in a different color, minus 3/5 g big M squared over r. So now basically what we want to do is solve for r, and the way we're going to do that is, I suppose earlier I was being a bit sloppy with my language. What we want to find is the minimum radius, essentially, that our white dwarf with the mass of, say, the sun could be. And the way we're going to do this, this looks awfully terrible. I will say that the amount of just constants we have in front of our r's it's quite horrific. But one thing that we really can do to clean things up a bit is say, well, what if we just say A is equal to everything, except for the r squared in that term, and B is equal to, everything except for that R right there. Basically meaning that our A is just going to be, well, this mess right here. And our B, which I'll actually write out, is just going to be negative 3/5, or actually, sorry, positive 3/5. We want to keep the negative sign in there. It's going to be 3/5 GM squared. So what we have now is just, this is kind of, I hesitate to use the word classic, but this is like a Calc 1 minimization problem. What we have is some, we have some like function of R, or I'll use E of R, I suppose. We have our energy in terms of R equal to A over R squared minus B over R. And all we want to do now is just find, well, the minimum. Well, that's where the derivative is going to be 0. So that's actually not too terrible. So just differentiate both sides and set it equal to 0. We have then A, but then we have negative 2 out front because of the power rule, over R to the 3 plus B over R squared. And that is just equal to 0. Meaning if we just solve for R here, I'm just going to multiply both sides by R to the third, we end up getting negative 2A plus BR is equal to 0. And it's rather straightforward. I hope we can solve these equations. All we have then is just R is equal to 2A over B. So now that we found our minimum radius, what we can essentially do then is take this right here, calculate our A and our B numerically, and find the minimum radius for a white dwarf with the mass of the Sun. But before we can plug and chug, as some say, we have this little term here. We have ND. And I believe I already noted this, but we have to note that D has to equal 1/2. And this basically means that for every 2 nucleons, so that's like for every proton and neutron we have 1 electron. But also one thing we have to note is that this little n right here, we said that n earlier was basically our number of nucleons, but how on earth do we know how many nucleons we actually have, within the Sun? And the answer to that really isn't all too terrible. It's just going to be the mass of the Sun divided by the mass of, say, a neutron. So that's just or mass of the neutron. I'm not going to add in any numerical values here, simply by virtue of it's going to make everything incredibly messy and just not very nice to look at, even more so than it already is. But whenever you do end up plugging in all of these values, you get some very large numbers, but they do actually kind of cancel, which is very nice. So for A right here, we end up getting 5.75. Which isn't too bad, but then you get the little, 10 to the 10 to the 56, which is quite a big number. And for this right here, for this B, we end up getting something that's slightly smaller, I suppose. We end up getting 1.6 times 10 to the 50. So with our numerical values in, what we need to find is 2A over B, and that's going to be our minimum radius. And when you plug everything in, we end up getting 7.18 times 10 to the 6 meters, which really isn't, that, which is right, but it's not that much different than the radius of the Earth, which let me the radius of the Earth, stop giving to me in miles. Okay, the radius of the Earth is 6.4 times 10 to the 6, so it's really only slightly larger than the radius of the Earth, which is, significantly smaller than, just the Sun. But one thing I did say at the beginning of this video was that I didn't want to just do this for a white dwarf. I also wanted to do this for a neutron star, and we can do that. The only difference that we're going to have to note is that instead of this d here being a 1/2, this d, I don't think I wrote it down anywhere. Yeah. This d, instead of being 1/2, this has to be equal to 1 now. Basically because we're relying on neutron degeneracy instead of electron degeneracy, and also our m in the denominator here, so this little m right here, this is now going to be equal to the mass of a neutron instead of the mass of an electron. So with that in mind, we can now calculate our new values of A and B. What we find when we plug everything in numerically is that our A is equal to 9.95 times 10 to the 53, which is slightly smaller than what we had up here, but that makes sense a little bit because the mass of our neutron is slightly greater than, we're dividing by it, so it makes sense a little bit. But our B is actually just going to remain the same, so our B is just going to be 1.6 times 10 to the 50th still, and that's just because the gravitational potential energy of the sun, or sphere in this case, our white dwarf, or neutron star actually, that's not changing because it's not changing. The only thing that's changing is the radius, so that little coefficient there is just going to stay the same because we're assuming it has the same mass as the sun. So what we end up getting, all in all, 2a over b. That right there, this is actually kind of funny. 2a over b is just 12,437.5 about meters. And that right there, for reference, is just 12.4 kilometers. I mean, if you're really dedicated, you could just run that. I mean, it's really not that far. I definitely drove more than that today. But point is that a neutron star is much more dense than a white dwarf, which is quite interesting. So anyway, this is a video a bit longer than I probably wanted, but that's okay. I had a great time kind of deriving the radius of a neutron, or minimum radius of a neutron star in white dwarf. Anyways, at any rate, I hope you all enjoyed this video in this edition of Physics Friday. There will hopefully be another video out tomorrow, but we shall see. Anyways, thank you again, and I'll see y'all in the future. Adios!